All right, class, welcome back. This week in 220A, we're going to continue our discussion on partition functions, exploring their utility and generalizing them a little bit to other sorts of constraints you might encounter. So we've previously introduced a notion of a partition function for a system that can exchange energy as a normalization constant for the Boltzmann distribution. Today, after we expand on that a little bit and rework through some of the examples we encountered last week, we'll generalize that notion to a case where not only the temperature is fixed, but also the chemical potential. So a case where the number of particles in the system can fluctuate. That'll put us in a position, having expanded upon the utility of partition functions, to later on this week in the next lecture discuss a little more precisely how you would go about computing partition functions for systems which are slightly more complicated than the lattice models we've encountered thus far. But to start, let's go ahead and review some of the important concepts we've been introduced to last week. So one of the most important things we discussed was the notion of an auxiliary function. A function invented in order to allow for other variables other than the extensive quantities entering into the first law to be manipulated. So specifically, we begin with an expression for the energy, which tells us that it is a natural function of things like the entropy through the heat term, TdS, and mechanical variables in chemical systems being volume and number of particles. So taking this as a starting point, we noted that it's kind of awkward to think about making displacements or changes, differential changes to the entropy. Usually one imagines in experimental setups fixing out the entropy, but maybe the temperature. And so we constructed functions like the Helmholtz for energy, which took that energy and subtracted off the conjugate variable pair T times S, the entropy times the temperature. And what results is a natural function of the volume and number of particles, but rather than the entropy, like the energy depends naturally on, the Helmholtz for energy is a natural function of the temperature. Generalizations of this so-called Legendre transform for things like the Gibbs for energy, which is a natural function of the temperature, pressure, and number of particles, are constructed analogously to exchange the role in the energy of the temperature and entropy. You subtract off T times S, and to change the role or the dependence on the pressure from the volume, we would add P times V, adding because P enters into the first law with a negative sign. To end up, we also introduced the so-called enthalpy, denoted H. So it's a natural function of the entropy, pressure, and number of particles by, you guessed it, taking the energy and adding P times V. Each of these functions, therefore, encode different sorts of physical systems where temperatures or pressures are being held fixed, and through which there are simplified expressions for things like the second law that we can write down. So entropy increasing in a closed system is a natural way to state the direction of a spontaneous fluctuation, but not all systems are closed. If we instead, for example, hold the temperature fixed, the natural way to discuss spontaneous change is through the Helmholtz for energy. If we hold both the temperature and the pressure fixed, the Gibbs for energy is what's going to tell us the direction of spontaneous change. Okay, so just like we can invent auxiliary functions that depend naturally on different variables, we've introduced microscopic connections between those auxiliary functions. And in particular, we've noted that the so-called partition function for a system in contact with a bath at temperature T is defined through the Boltzmann distribution, namely in such a system in contact with a bath at temperature T, thereby admitting the exchange of energy between the system and the bath, the probability of observing a microstate is exponentially suppressed in the energy of that microstate. With a normalization constant we've now introduced as capital Q, as a normalization constant, then it can be computed by summing over all the possible outcomes, in this case, all the possible microstates, weighted by those exponential factors. So that is essentially the definition of the partition function entering in pragmatically as a normalization constant, and yet it, as we've seen, contains loads of information. For example, we refer to it as a partition function because it tells us the probability of observing collections of microstates, partitions of microstates, relative to each other. So for example, if I consider the probability of seeing a group of states B relative to a group of states C, that is equal to a ratio of partition functions for those groups of states B and C. That then primes you to start thinking about, well, the probability of seeing one group of states relative to the other, that's maybe not so far and away from something like a concentration of those states, a relationship we will explore in a few weeks. But it makes you think that, well, you know another quantity that tells you about likelihoods of things or concentrations of reactants or products, and those are free energies. And indeed, we derive that the partition function exactly codifies the Helmholtz free energy. It is equal to the exponential of minus beta of the Helmholtz free energy. Rearranging then, one could say that the Helmholtz free energy microscopically is nothing more than KBT, has energy units, with a minus sign log of that partition function. So it encodes thermodynamic information, it encodes ratios of probabilities. Finally, we also noted that it acts as a cumulant generating function. That's a fancy way of saying that if I take the derivative of log of Q with respect to minus beta, fixing in V, the other natural variables of Q, we will have computed the average energy of the system. Similarly, if we take two derivatives of log Q with respect to beta, as a cumulant generating function, a second derivative generates the second cumulant, i.e. the variance of the energy, which we've noted in a pretty exciting demonstration that that fluctuation in the energy is nothing more than kBT squared, the heat capacity of a system, thereby establishing a microscopic relationship between a thermodynamic response function, how the energy changes or responds to a change in temperature, and a fundamentally microscopic quantity like how large the fluctuations in the energy are. So that's all to convince you that partition functions are useful. We have then demonstrated at the very end of the last lecture how you go about computing them. For example, for a non-interacting system, one for which the energy is expressible as a sum of energies of the individual components, the probability of a microstate in such a system factorizes into probabilities for the individual components, be they particles, lattice sites, etc. And as a consequence, the partition function takes on a very simple form. It factorizes as well into n products of a single particle partition function. So indeed, in a non-interacting system, if we can sum over all the states corresponding to an individual particle at fixed temperature, we thus can compute by taking n factors of that single particle partition function, that single particle normalization factor, the partition function for the whole system. Okay, so that was a bit of review. I want to keep reviewing a little bit more. I want to go back over those partition function calculations we did in the context of non-interacting spins to remind ourselves that this partition function Q encodes the same information as our old friend omega, the number of microstates for an isolated system, that doing calculations at fixed temperature, fixed energy are thermodynamically consistent with each other, at least in the limit that the system is large. So to remind ourselves of that by a couple explicit calculations before we go on to generalize these notions a little bit by opening the system up to exchanges of particle number, not just energy. Okay, so let's start there. Back to our non-interacting spin system. So we are envisioning a system of spins, say on some one-dimensional lattice. Those spins are denoted with these little arrows. They can be up or down. If they're up, we'll call that spin is +1. If they're down, we'll call that spin -1. We will impose a preferred direction by applying an external field that makes it energetically favorable to a line in the up direction, and that field will have some magnitude epsilon. So if we're going to go about computing the partition function for the system, the first thing we need to note is how do we describe the microstate of the system? What is the information I need to supply in order for you to completely know what each degree of freedom is doing? In this case, that microstate is determined by all of the spin variables. So whether or not spin 1 is up or down, spin 2 or up or down, all the way up to spin n. That's the full microstate of the system. That's the thing we'll have to sum over. And then I need to give you the energy function, so you know what to weight that probability of that microstate by. And for a system of non-interacting spins, we've posited that a reasonable way to represent that energy would be that aligning interaction with magnitude epsilon over 2, applied by the field, and then acts on each individual spin by itself. Thus, the total energy is decomposable into a sum of single spin energies, where that single spin is multiplied by the applied magnetic field. So in such a system at fixed temperature, the probability of the state, as we've just reminded ourselves of, factorizes. And so I am free. So if I wanted to know the probability of S1, S2, all the way up to Sn, all of those spins act independently. So the probability is just the probability of S1 times the probability of S2, all the way up to the probability of Sn. And thus I can, all spins being equal, completely determine the state of the system, or the statistics of the system, by working out statements about an individual spin. So let's call some tagged spin that I'm curious about S, the probability of S is proportional to a Boltzmann's constant, e to the beta epsilon by 2, the variable S, whether it's plus or minus 1, and it needs a normalization constant, Q, to be determined. I can work out what Q is by noting that I have to sum over all the microstates of an individual spin. In this case, S can either be plus or minus 1, weighted by those Boltzmann factors, like so. There are only 2 terms in that sum, so what I arrive at is a sum of exponentials with opposite signs in their arguments, like so. So thus, I have a complete representation of the probability that a spin is up or down. Which means, for example, I can compute the average value of a spin. It's going to be a sum, again, over whether or not that spin is up or down, all outcomes, the probability of that outcome, times the value of that outcome. And as we arrived last time, I'll take the difference of exponentials with opposite signs in the argument over a sum of exponentials with opposite signs in the argument, which is nothing more than hyperbolic tangent function. Okay, so we've seen this before. Some of the steps are done in a little more concreteness, showing you exactly how you compute that single particle partition function, acknowledging the factorization of this system in the case where the spins are non-interacting. So again, the fact that the energy is a sum of individual spin variables weighted by factors that are constant endows the rest of the calculation with this same structure, the factorizability of the probability of a microstate and the product form of the partition function, allowing us to compute the average value of a spin. Let's go ahead and highlight that, this hyperbolic tangent function. If I wanted the total net magnetization, well, that's simply computable by the average magnetization of one specific spin. The total magnetization, the average total magnetization, is an average over a sum of the individual spin variables. If all of the spins are the same, the total magnetization would just be n times that average S. So indeed, I really do have global information from this calculation. Now, as alluded to last time, we could have alternatively attempted this calculation say, tried to arrive at the average value of S in a system with fixed E. If we do that, our life is going to be a lot more complicated. The calculation is more cumbersome for the reason that an individual spin is no longer statistically independent of all the other spins due to this constraint that the total energy has to be fixed. So if I fix the total energy and I tell you what one of the spins is doing, I have imposed that all the other spins have to act in such a way, have to be in such an arrangement, such that that energy is fixed. So there is correlation in the statistics of the spins at fixed energy that are not present at fixed temperature. Nevertheless, we can work out that calculation, and the way to proceed is to note that the typical arrangement of the system will be that which maximizes the entropy if I allow for that magnetization to change. And so if we can compute the energy, the entropy, and maximize it, we can find the value of the spin that does so. Okay, so maximizing the entropy is doing nothing more than counting up some number of ways the system can exist at fixed energy. And to do that, we need to be able to write down how the energy is related to a specific arrangement of spins. So if we take our initial expression for the energy as minus epsilon by 2 times the sum of spins, well, all that really matters is how many globally are up, call it an up, and how many are globally down. Those two numbers are not independent. I can know how many are down by knowing the total number of spins and subtracting off the number that are up. Rearranging this by pulling out n and a minus sign, I find that the energy is expressible as n times epsilon over 2 multiplied by 1 minus twice the fraction of spins that are up, which we'll denote little f and define as n up over n. So there's a one-to-one mapping between the energy of the system and the fraction that are up. So if we fix the fraction, we fix the number that are up, the energy is identically fixed. That makes our life easy because then counting the total number of states, omega, boils down to just counting how many ways I can arrange n up spins on a lattice of n total spins. That's a combinatorial problem you've run into a number of times already this semester. It is given by a binomial coefficient n factorial over n minus n up factorial with this permutation of n up factorial. And the entropy follows just through Boltzmann's definition, kb log omega. Now we want to maximize that entropy, which is not so simple to do if we're imagining that those factorial functions are defined on the are defined for integer n. That's not a nice smooth function, but there's a limit where we can approximate that factorial function to be something smooth and easy to differentiate, and that would be a large n limit. So provided n and n up are both large, we can employ the coolest approximation in statistical mechanics, due to old Stirling. We can use Stirling to say that log of n factorial is nothing but n log n minus n. We have to do that a bunch of times for all the different factorials that enter into that omega. So that just gives us some algebra to do. Doing so, we find that the entropy is well approximated by kb times n log n minus n minus quantity n minus n up log n minus n up minus n minus n up plus n up log n up minus n up. That's a mouthful. Simplifies quite nicely. There's a factor of n up with a minus and with a plus there. There's a minus n and a minus n. Those all cancel. So we only have log functions left. Going through that algebra, pulling out a total factor of n, we find that the entropy can be expressed as f log f plus 1 minus f log 1 minus f. Must be something not quite right because f is a number less than 1. If we take a log of something less than 1, we get a negative sign. 1 minus F is also something less than 1, so that should be -2. We know the entropy as a number of microstates has to be positive. Must be a minus sign out here. All right, so that is the entropy. We can now maximize it with respect to the energy to find the most likely state of the system. If we do this, say with respect to the energy, well, it's most convenient to do that partially with respect to the fraction of spins up. We have an explicit expression for how S changes with F. We also have an expression for how E changes with F. So if we introduce through a chain rule that dependence on F explicitly, that'll give us something easy to compute. So if we work out this one first, so E is equal to constants times 1 minus 2F. If I take the derivative with respect to F, so E equals epsilon by 2 in 1 minus 2F. Taking the derivative with respect to F, we get a 2 and an epsilon. The 2's cancel. We need an N and an epsilon and a minus, and F goes away, leaving us with 1 over N epsilon with minus sign. Taking the derivative of the entropy with respect to F, get a minus, a KB, and an N. Now a bunch of chain rules, but this will all simplify to log of F minus 1 over 1 minus F. Nice and simple. So we put that in there. So ds, maximizing the entropy with respect to the energy, and reminding ourselves that that is nothing but the definition of the inverse temperature. We find that the inverse temperature in the most likely arrangement of the system, that which maximizes the entropy, is satisfied by taking the product of these, this term and this term. Minus signs cancel, the n's cancel. I have a KB, a n's cancel, excuse me. I have an over epsilon. I have a log F over 1 minus F. So that is a condition that must be satisfied in the most likely arrangement of the system. That is not so easy to look at. We can rearrange it. So if we bring epsilon and KB over to the other side, we have epsilon KBT. We take an exponential of that, so that gives us F over 1 minus F. We can solve for F. That gives us F is equal to e to the plus beta epsilon over 1, minus 1 plus minus beta epsilon. So the fraction of up spins satisfies this simple relationship in the most likely arrangement of the system. That's not quite what we worked out before. We didn't ask for the fraction of spins up. We asked for the net magnetization of a single spin. But these two things are related. S is nothing but 1 minus 2F. That follows from this equality. That's the net magnetization per spin. So if we plug in F, we've just got 1 minus twice e to the minus beta epsilon 1 plus beta epsilon. We find a common denominator. This is nothing but 1 plus beta epsilon minus twice minus beta epsilon over 1 plus minus beta epsilon. One of these cancels that. 1 plus e to the beta epsilon over 1 minus beta, 1 minus e to the minus beta epsilon over 1 plus e to the minus beta epsilon. If I multiply top and bottom by beta epsilon over 2, that then gives me a difference and sum of exponentials with opposite signs in the arguments, which is then, again, just our hyperbolic tangent function. Nothing more than what we found before, albeit in a much more cumbersome calculation. Well, that's nice. So indeed, this is an explicit demonstration that in the large n limit, where means dominate over fluctuations, we do indeed find that Q contains the same information as omega. We computed omega explicitly and manipulated it in a set of concrete mathematical operations to find the same answer or relationship between the temperature, epsilon, and the average magnetization of a single spin as we did through the calculation where we explicitly computed Q. So to kind of take a step back and reconsider both of those objects, Q and omega. Omega is an object that encodes information about a system at fixed energy. Under conditions of fixed energy, the probability of a microstate is just 1 over omega, where omega is defined as the number of microstates, given this constraint that the microstate has a given energy, as well as additional constraints on the mechanical variables. If we can compute that quantity, omega, it gives us access into thermodynamics. It tells us what the entropy of a system is through taking a log and giving it units. Entropy has units of Boltzmann's constant, energy per Kelvin. The log is something we uncovered. It had to be a log. It's not just an educated guess by Boltzmann. It had to be a log because the number of states is something we expect to grow exponentially with the scale of the system. Thus, if I take the logarithm of that omega, the entropy then is expected to grow linearly with the scale of the system, consistent with our expectation that the entropy is an extensive quantity. The distribution of microstates that a system can sample under fixed energy, we refer to as an ensemble. So a distribution of microstates in general would be referred to an ensemble, as an ensemble. And under conditions of fixed energy, we would call this the micro-canonical ensemble. This is to be contrasted with the case of, rather than fixing the energy, fixing the temperature, whereby we found that the probability of a microstate now takes this Boltzmann exponential form with a Q, which is again just a normalization factor. This case looking a little more complicated because states are not equally likely under conditions of fixed temperature. Let me clean this up a little bit. But again, if we can compute that Q, that normalization constant, that partition function, by performing that sum, we get access into thermodynamic information in analogy with the Boltzmann definition of entropy, albeit this case through the Helmholtz free energy. Namely, if we give units of the Helmholtz free energy as kBT, a thermal energy scale, and take the log of Q, we arrive at a microscopic definition of the Helmholtz free energy as just the log of the partition function under fixed T, the partition function in this case being that of the so-called canonical ensemble. Canonical because it is often the case in traditional statistical mechanics that the temperature is held fixed in addition to the volume and number of particles. That is the ensemble most often constructed or considered. So this little discussion should impress upon you that there's nothing really special about a closed system, given that initial definition or postulate. We can thus derive equivalent statements of likelihoods of microstates through straightforward means. Fixing the temperature as opposed to the energy is just one. You should then be curious to ask whether or not there are others. There are other constraints we can impose and understand their consequences for the likelihoods of observing specific microstates. And indeed, there are an innumerable other sorts of conditions we can imagine. For concreteness, and to remind you kind of how we got to this Boltzmann distribution, let's consider a case where both the energy and the number of particles can fluctuate. What is the corresponding probability of observing a microstate in such a case? So to do that, we need to remember how we got that Boltzmann distribution. So we run back to our isolated system where things are straightforward to describe. In a system that is rigid, so its volume doesn't change, it's impermeable, so the total number of particles don't change, and insulated, so the energy doesn't change. The probability of a microstate in this box is just a constant. Within that box, however, we can pick out a region we're going to focus on, call that the system. The surrounding part we'll call the bath, and let's imagine that the way that the system and bath interact is through the exchange of energy and number of particles. Now, there is a total energy in that brown box, which is going to be equal to whatever the energy of the system is, which depends on whatever microstate the system is in, and must add to that some energy of the bath such that that total energy is conserved. And we'll denote the energy of the bath, EB, and the corresponding microstate of the bath, nu B. Analogously, there is some total fixed number of particles, which is given by a sum of the number of particles in the system, plus the corresponding number of particles in the bath, which will denote NB and microstate nu B. Now again, everything in the brown box is an isolated system, so the probability, if I specify both the state of the system and the state of the bath, is just a constant. All states are equally likely. But as before, if we are interested in just the system, the probability of observing just the system, irrespective of what the bath is doing, is going to just be proportional to the number of ways the bath can exist, such that the constraints globally are satisfied. So I need to specify that the energy is fixed by noting whatever that state of the system is. If I take it, subtract it off of the total energy, that specifies a bath energy that has to be set and determined. And analogously, the total number of particles less that the number in the system has to be the corresponding number in the bath. So if I set the energy of the bath and I set the energy of the number of particles in the bath, I can count up how many microstates are consistent with that energy and particle number, and that will give me the probability of a microstate in the system. The likelihood of observing a state of the system is just given by the number of ways it could happen, which in this case is just the number of ways the bath can exist given that stated arrangement in the system. Now again, let's imagine a limit where the bath is really big, such that the energy of the system relative to the total energy is small. And similarly, that the number of particles in the system is really small compared to the total number of particles. In such a case, even though we don't want to try to compute the number of microstates of the bath, we can get its form by treating the energy of the system and the number of particles of the system as a perturbation. So for a large bath, as you've convinced yourself in your homework, it behooves us to expand log of omega b instead of omega b directly. If we expand log of omega b, we'll have a rapidly converging series, the 0th term of which is just a constant independent of the state of the system. The first order correction takes the small parameter, the energy of the system, in this case with minus sign, and asks how does that change the number of states in the bath with respect to the energy of the bath. This is then at fixed number of particles, all the mechanical variables. D log omega dE is what we've called beta. 1 over kBt through the identification of log omega being the entropy, and how the entropy changes with energy is just the inverse temperature. Analogously though, we're imagining that the number of particles in the bath is small, so there's a first order correction there. Which is weighted by how the number of particles change the number of microstates in the bath. And there are higher order terms. Now this term is how the entropy in units of Boltzmann's constant changes with particle number. And thermodynamically, we know what that means. That is nothing but minus beta mu. So we find, maybe not unexpectedly, a product of conjugate variables entering into the description of the likelihood of the state of a system, namely N, the number of particles, and mu, the chemical potential, which sets the potential for spontaneous change in that number. So putting those two things together, the probability of a microstate in the system exponentiating the log of omega b is just a constant. Call this constant capital C, terrible but typical way of denoting this normalization constant. We get a minus the energy of the system and plus beta mu, the number of particles in that microstate of the system. So now we find something exponentially suppressed in the energy and exponentially enhanced by beta mu times the number of particles in the system. This normalization constant is another partition function, the one which is a natural function of the temperature, chemical potential, both of which are explicit in the exponential, and the volume, which enters into the microstates that we're still holding fixed. That partition function, as all of them can be, is expressible as a sum over microstates weighted by that exponential factor. In this case, beta E plus beta mu n. You can give this a fancy name. It's called the grand canonical ensemble. Heaven knows why. I think it's due to Gibbs. So what, your eyes and ears should be perking up. Yeah, there's another ensemble, there's another partition function. There's probably lots of interesting relationships we could uncover with that partition function. Indeed, you would be exactly right. For example, rewriting that sum as capital C by grouping particles, or by grouping microstates in terms of all of those with a fixed number of particles, because remember, the number of particles is a fluctuating variable now. We can first sum over, ooh, those are terrible sums. Let me try that again. We can first sum over microstates with a fixed particle number, and then sum over all particle numbers. So we can do that sum in those two steps. If we do that, a sum over microstates at fixed n and b, weighted by that Boltzmann factor in the energy, that's nothing but Q. So this can then be written as a sum over n Q times this additional factor, which again, this is constant, you can go through the sum, beta mu n. So look at that, the same sort of structure as we found between omega and Q, namely that of a Laplace transform. Is uncovered. Namely, the grand canonical partition function is nothing but the Laplace transform of the canonical partition function, with that Laplace variable being beta mu. All right, so the fun doesn't stop there. If we take a large system limit, that sum is going to be dominated by its most likely value. Fluctuations are suppressed. So we can take that most likely value and pull them outside of the sum. We would find that that partition function can be approximated by that most likely energy less Ts. That's the canonical partition function, with an additional factor of mu and that most likely number of particles. So E minus Ts minus mu n. What is this? Well, I will assert that the energy can be written as Ts minus PV plus mu n, namely what looks like the differential form of the energy, though integrated. If that is true, rearranging, we have E plus Ts minus mu n. Sorry. Minus Ts is equal to minus PV. Hey, that's exactly what we have in that exponential. This is this, which means that this partition function must give us information on beta PV. just another thermodynamic equivalency between the partition function under a set of constraints, in this case fixed chemical potential, volume, and temperature, and a corresponding thermodynamic potential, in this case the pressure times the volume. To which you should think, well, what happens if you take a derivative of that grand canonical partition function? Is that interesting? Absolutely. If you take a first derivative of log of c with respect to beta mu, one of the variables it is a natural function of, and hold the temperature and volume fixed, let's see what we'll get. Derivative of log through the chain rule gives us a factor of 1 over that function. Putting in what we mean by that grand canonical partition function as a sum over microstates, e to the minus beta energy of that microstate plus beta mu, the number of particles in that microstate. Again, the temperature is being held fixed. So we're really taking the derivative with respect to mu and have a factor of 1 over beta hanging around. If we bring this derivative inside, you'll note we'll pull down a factor of the number of particles in the microstate. So we'll have a sum over microstates, the number of particles in that microstate. If we bring in that factor of 1 over the partition function, we'll have e to the minus beta e nu plus beta mu in nu over that partition function. That is nothing more than the averaging operation. The probability of the microstate is just this. So if I sum over all possible outcomes, the probability of that outcome, that is the averaging operation. In this case, the average is taken of the number of particles. So we take one derivative of this partition function and we get back the average number of particles in the system. I'm sure your excitement is just bursting to see what would happen if you take two derivatives of that partition function. I'll appease you. If you take two derivatives of this grand canonical partition function with respect to beta mu, holding temperature and volume constant, you should be able to show that you will generate the fluctuations in the particle number. That should be intuitive if you note that the grand canonical partition function is another cumulant generating function. The first derivative generating the first cumulant, average number of particles. The second derivative generating the second cumulant, the variance in the number of particles. And just as before, we can take two derivatives and get that variance, or a derivative of the derivative, namely how the average number of particles changes with chemical potential, holding V and T fixed. So again, we've arrived at a fluctuation response relationship, in this case, illustrating a relationship between the particle number fluctuations and how the number of particles change on average when I tune the chemical potential. Now that is not something that is naively intuitive, I think, or is not intuitive. It's not something that you can imagine doing a simple experiment to measure how the average number of particles changes with chemical potential. I don't have a chemical potential knob on my experimental apparatus here sitting at my table. I can imagine how I might tune the temperature. Chemical potential is more difficult. So it behooves us a little bit to take a detour back into thermodynamics to understand what this response function actually is telling us. Let's do that. Take a little detour. Again, I have express the energy earlier as T times S minus V times P plus mu dN. Now, I have not derived this for you. It is derivable. There is an important assumption in integrating the energy to give this form. Anyone who is interested should ask me in the live session. I'll be happy to demonstrate what is required to get this relationship. However, if you accept that that's true, one could ask what happens if I take the total derivative of this energy. dE, the total derivative is the total derivative of the right-hand side, which has a whole number of terms that don't look like they were around the first time. Namely, I'll get a T ds, but I'll also get an S dt. I'll get a minus P dV, but I'll also get a minus V dP. Similarly, I'll get a mu dN plus an N d mu. Now that does not look like the first law I was raised to believe in. If that first law was correct, which indeed it was, it must be that dE is by itself equal to T ds minus P dV plus mu dN, implying that the remainders S dt minus V dP plus N d mu must themselves sum to 0. Now, this is an interesting sort of relationship because it now relates differential changes in our potentials, in the fields, in the temperature, pressure, and chemical potentials. All intensive quantities. Indeed, we can write this lacking any sense of scale by introducing little s as the entropy per particle and little v as the volume per particle, to which we, when substituting those in, arrive at an equation that relates the chemical potential to changes in temperature weighted by little s and changes in pressure weighted by little v. This equation has a fancy name. It's known as the Gibbs-Duhem equation. Since it's got a fancy name, let's put a fancy box around it. Oh, that's a terrible box. Looks kind of like Tennessee. Yeah, there we go. Okay. So why did we go through and derive the Gibbs-Duhem equation? Well, because the Gibbs-Duhem equation will give us insight into what this factor here means. dN d beta mu at fixed v and t. If I pull the beta upstairs and multiply and divide by a factor of the volume, which I can do because the volume is fixed, gives me dv in by v d mu at fixed v and t. That is nothing but the density. And the Gibbs-Duhem relationship tells us that d mu at fixed temperature is equal to little v dP. If you don't believe me, look up there. I fix the temperature. The S dt term goes away. I'm left with just that, which is rewriting rho d mu is equal to dP. So I can exchange the differential with respect to mu with a differential with respect to pressure at a cost of the density. Now note, this, when I introduce rho, KB T V d rho d mu, constant T, I no longer need to say constant volume because there's no scale in this problem. So now I can put in a factor of dp for d mu at a cost of rho. So d in d beta mu at fixed v in t is thus equal to kbt v, that factor of rho, d rho dp at fixed t. I could do some magic and say, well, instead of taking the derivative at fixed n, I can take it with respect to fixed v. That generates, so first, this is nothing but, I don't want to do that. So I could remind myself that this is n over v, and I can take it with respect to v, which gives me a factor of minus kbt v rho over v dv dp. Now this is at fixed n and t. How the volume changes with pressure, that's something I can imagine actually measuring. In fact, this is given the symbol kappa T and is known as the compressibility. So dn d beta mu is up to factors the isothermal compressibility. So done at fixed temperature, thus isothermal. It's defined with a minus sign and pulling out that factor of v. Let's clean that up. So the compressibility, that is this, this, and that. That's how it's defined. So indeed, a observable response function, how the volume changes with pressure, is related to a fluctuation quantity, how the particle number fluctuates. That's a benefit of this grand canonical partition function. We have access to this in a simple way. So that's our detour. Let's get back on track. Let's imagine asking now how we actually compute things within the grand canonical ensemble. Let's revisit the lattice gas we considered in the very first lecture of class. Lattice gas part 2. So if you remember all the way back then, I did this silly beaker experiment with diffusion to illustrate direction of spontaneous change. The idea or the setup being we have some liquid and some number of solutes that were dilutes. And we wanted to understand some of the physical properties of that system. So in this case, let's pick out some piece of this beaker. Let's call that piece the observation volume. Capital V. And as we do, let's imagine considering this volume gridded up into little cells. Now within any one of those cells, maybe there's a particle, a solute going into that cell. And if there is, we'll assign some fluctuating quantity, little n, for that cell I with the variable 1, or with the number 1. So there's a particle in that cell. If, however, that cell is empty of a solute, will associate with that cell a little n of 0. And let's imagine that we have m number of cells. These are really hacky. Let's make that a little cleaner. There you go. And we'll assume that those solutes are dilute. So such that they are very unlikely to notice each other, to run into each other, and thus the energy of the solutes do not depend on the particular arrangements of those solutes. So if there's no interaction energy between the solutes, it is just some constant that doesn't change. So whatever that constant energy is, it's just a number, and we'll set it to 0 for convenience. So the energy of any state of the system, any arrangement of those solutes in our grid is just 0. However, as pictured, you could imagine that solutes come in and out of that beaker, or not of the beaker, they're stuck in the beaker, but in and out of that observation volume. But we have a convenient way of counting those solutes, and that's just by summing up these little binary variables that run between 1 and n. That's the instantaneous number of particles in our volume. This is again assuming that because it's dilute, the likelihood that there are multiple occupancies in any one of those cells is sufficiently low that it's negligible. So just as when we compute the canonical partition function, we need to specify things like the energy function. Here, we need to specify the energy function, how to compute the fluctuating number of particles. Both of those we've explicitly written down now. The last thing to note, if we're going to sum over microstates, is what defines the microstate of this system. And in this case, it's just a sequence of binary variables that tells us whether or not each cell is occupied or not. Okay, so that's the setup. So the grand canonical partition function then is written as a sum over microstates weighted by the energy of that microstate, which is 0, and a fluctuating number of particles multiplied by beta mu. Now, that microstate can be summed over by summing over cell 1 being 0 or 1, cell 2 being 0 or 1, all the way up to the nth cell being 0 or 1, all weighted by e to the beta mu. Now the sum over the number in I from 1 to n. Now note the structure. Just as before, when the energy is expressible as a linear sum of the individual fluctuating components, here too, when the particle number is expressible as a sum, when I take e to that sum, I get a product of exponentials. So this could be written as e to the beta mu n1 times e to the beta mu n2, etc. And thus each one of those terms can be associated with its own individual sum. So I can put that one there. I could put this one here and do the exact same thing for each one of those terms. So the whole thing factorizes. Which means that the whole partition function is just m factors of a sum over what a single cell is doing. So it'll have some form of some number to the m. This sum is easy to do. It has two terms. The first one, when I put n1 is 0, is just 1. The second one, when I put n1 is 1, is just e to the beta mu. Let's call that e to the beta mu z. And note that that is often called the activity. All right, so we've computed the partition function. It is just 1 plus e to the beta mu raised to the m. What can we do with it? Well, if we take a derivative, we know we're going to get something interesting. The average number of particles in that observation volume is computable by taking d, that partition function, with respect to beta mu. That will give us log of the partition function brings out a factor of m. 1 plus, let's write this more succinctly as 1 plus z. Taking the derivative with respect to beta mu, thus gives me an e to the beta mu, what I've denoted z, over 1 plus e to the beta mu, again, what I've denoted as z. So there's the average number of particles expressible as a function of this activity, which is nothing but a complicated way of writing the chemical potential, or e to the beta chemical potential. If we let F be the fraction on average of occupied cells, average N over M, I can move this M to the left, and I find that F is nothing but Z over 1 plus Z, which lets me solve for Z in terms of F, which is just F over 1 minus F. Remembering that Z is nothing but e to the beta mu, that tells me that beta mu, taking log of both sides, is nothing but log F over 1 minus F. That should look a little familiar. That sort of functional dependence on the fraction is something we'll see again and again. Comes out, as you might expect, as a statement of non-interacting systems generally. It will behoove us to note that we could have written this expression in one other way, as 1 plus Z is equal to 1 minus F. Namely, that if I take 1 plus Z up here, the partition function is a simple function of just the fraction of occupied cells in this case. That's useful because if we remember that the grand canonical partition function is nothing but e to the beta pressure times volume, by computing that partition function, we have information on the equation of state of this lattice gas. It's a functional relationship between the pressure, volume, and quantities that are computable in the system. So specifically, if we put in that beta PV is equal to log that partition function, as we've just noted, we could substitute 1 plus Z here. And so we have log of 1 minus F to the minus M. So beta PV is equal to minus m log 1 minus f. If f is small, which is our low density, low concentration assumption. So in fact, all of this is predicated on f being small. If f is small, the log of 1 minus a small number is minus that small number. So beta PV is m times f. F was average occupancy. So what have we just found? That PV is equal to NKT. No surprises there. The ideal gas law comes back out again. Again, a statement of statistically independent density fluctuations. That's all the ideal gas law is. Now note, we had previously did that counting and arrived at the ideal gas law all the way back in lecture 1 by working with a fixed energy, fixed particle number ensemble. Doing things here with fluctuating particle number, we still get the same results. Again, in the macroscopic limit, where the average value of n is expressible as the macroscopic n, namely that fluctuations are sufficiently small that we can neglect them. All right, that's just about all I wanted to say. So we've generalized this approach to statistical distributions under different sorts of constraints of fixed energy we know how to handle, fixed temperature, volume, and number of particles we know how to handle, fixed chemical potential and temperature. The variants are endless. What we have not yet quite undertaken is taking off the training wheels and working with systems that aren't just on a lattice. Our first stop on that journey is to consider more realistic gases, the simple of which could be just a single particle in a box. Say that box has length L, that particle is free to move, provided it stays in the box. Let's call that direction X. If I wanted to study that system under conditions, say, of fixed temperature, so the particle is surrounded by some bath, and I wanted to, say, compute its partition function, just a single particle, what its partition function is. Well, I could imagine that that particle is heavy, so maybe it's classical. In which case, the state of the system is just given by two numbers, where it is and where it's going, its velocity and position. If it's a point particle moving in this box, well, if it has velocity, it has kinetic energy. And I can keep it in that box, imagining that the box is infinitely hard. If I wanted to then fix, there's only one particle, fixed in N, I fix length and the temperature, I know that in principle I could compute a partition function by summing over the microstates. But now the microstates are X and Vx which gets a little awkward. Because now that sum has an infinite number of terms. There's an infinite number of places on the line I could put that particle. And the partition function being infinite is not so useful of an answer. So to move to more realistic gases, more realistic systems that live in continuums, the first thing we need to confront is how to do these sums. We need to expand our constructions to tackle such systems. And so we'll do that in the next lecture, both first phenomenologically, essentially imposing another scale, imagining we can squint and put in a lattice even when there's not one. And then by going back a step and actually acknowledging that the world is quantum mechanical, which we'll find introduces for us a scale. But that's all on Thursday's lecture, so stay tuned for that.